focuses on what we call predictive value of tests. The predictive value of tests is another phenomenon that is important in the area of validity of tests. Now, by way of background, in public health interventions, we are interested in screening populations, as I said, to find the people who are affected by the disease. They don't have symptoms, but we want to apply tests. No, they don't have clearly visible symptoms, probably, but we want to assess, to apply a public health screening test so that we identify them, so that they undergo remedial action in time. So we can apply a validated test, like we said. So we get a public health screening test, we validate it, and we roll it out. So that's one situation, and that's called screening. Now, in many public health interventions, we don't do screening as we know it. We don't first validate the test before we use it. We don't first validate the test before we use it. Rather, we apply the test, then validate afterwards. I'll give a very good example. If someone walks in with fever in a clinic in Uganda, someone comes and they have fever in Uganda, we ask them, what is your problem? They say, I had fever, I had, this. And then we take the temperature, we find the temperature is high. We may, using those symptoms, say that this person has malaria. And then we start treating them for malaria. So we have applied the primary care screening test here is the clinical assessment. The story that they have told us about their illness and the thermometer that we've used to measure the temperature, that is a screening test. And we say, this is malaria. But we don't know whether what we have done is correct. If we treat this person and they don't improve, then we are likely to apply the gold standard test, which is microscopy. So we say, oh, since you have not improved, we shall take your blood and now apply the gold standard. So in essence, instead of validating the test before, we validate our assessment after. And in such cases, we don't determine sensitivity and specificity, but instead we determine what we call the predictive value of the test. Now, the predictive value of a test is the probability that the test shows as having a particular condition actually have that condition. So it's the other way around. So it has two parts. There's what we call the positive predictive value. That is the proportion of those who test positive with your screening test. You're not sure that they have the disease, but with your test, they've tested positive. So the percentage of those who test positive with your test that in reality has the disease. Or we can, using probability approaches, is the probability that a person has a disease given that she tests positive with your primary healthcare screening test. On the other hand, the opposite, the negative predictive value, is the proportion of those who test negative with your primary healthcare screening test that in reality do not have the disease. So intuitively, you are first applying your primary healthcare screening test, and then you have those who are positive and negative, but you are not sure about their disease status. Then you apply the gold standard, and then you find those who actually have the disease. And I've said this situation is more common. When the clients come to a clinic, we first handle them presumptively using simpler tests. But if things don't improve, then we move maybe and we say, let's do a chest X-ray. So we are moving higher. If the chest X-ray does not solve our problem, maybe we say, let's do a full blood count, or let's do a CT scan. So we go higher towards the gold standard. So we validate after. And this is, as I said, is a little bit more common. So when we do that, we can summarize our findings in a 2-by-2 table. In a 2-by-2 table. So we've said we first do our public health screening test instead of doing the gold standard which determines those with disease and without disease, we first apply this test. And then it determines those who are positive and those who are negative. So in essence, those who are positive with our test is A plus B. And those who are negative is C plus D. If I go back to the on-screen illustration, you remember that for sensitivity and specificity, we started with the gold standard, and we determined those who actually have the disease and those who have no disease. Then we applied our primary healthcare screening test to determine those who are positive and negative. And then we denoted this as A, B, C, and D. So we say those who actually have the disease is A plus C, and those who don't have the disease is B plus D. So that's total. Now, if we work in reverse and first apply our public health screening test, those who test positive will be A plus B. And those who test negative with our primary healthcare screening test will be C plus D. Therefore, the probability of having the disease when you test positive is, that is the positive predictive value is A over A plus B. A over A plus B. While the negative predictive value is D over B, that is the NPV, is D over B plus D. So in essence, instead of looking downwards, we are now looking this way because we are starting with the public health screening test. So that is the positive and negative predictive value. Now, one thing to note that is very, very important is that unlike the sensitivity and specificity of a test that do not change, they are internal properties of a test. The positive predictive value of a test, when you start by the test and then you go backwards to the gold standard, the positive predictive value of a test changes. It can change. And there are two factors with which can change the positive predictive value. One, a change in the frequency of the disease. Once the frequency of the disease changes, the positive predictive value changes. Likewise, the specificity of the test. If you use a test, if the specificity of the test increases, then the positive and negative predictive values also change. And I will illustrate this with prevalence. Let's look at this example here. We have a population of 10,000 people. The test which we are using has a sensitivity of 90% and a specificity of 90%. The disease we are dealing with is malaria. The prevalence in this particular population we are dealing with is 1%. This is determined by the gold standard. So we apply the gold standard, and the gold standard tells us that the true prevalence of the disease is 1%. So 1% of 10,000 is 100. 1% of 10,000 is 100. So when we fill the 2 by 2 table, it means the people who actually have the disease are 100, so we put them down here with disease. And then without disease is 10,000 minus 100, which is 9,900. So that is that. Now, when we apply our test, we say the sensitivity is 90%. So 90% of the people with the disease is, 90% of 100 is 90, so the balance is 10. Now, the specificity here is also 90%. So 90% of 9,900 is 8,910, and that means the false positives are 990. So with this information, let us compute the positive predictive value and the negative predictive value. So the positive predictive value, we said, is this figure here over the total here, which is 1080. So 90 divided by 1080. While the NPV is this figure here divided by 8,920. And this is what we get. So the PPV, 90 over 1080, is 8.3%. And the NPV, which is 8910, It's supposed to be divided, this is an error, it's supposed to be 8200 times 100, which is about 99%. So that is scenario 1, 8.3 and 99.8. Now, let us look at a population where the prevalence is no longer 1%, but it increases to 10%. 10%. The test is still the same, sensitivity 90%, specificity is 90%. But the population size is still the same, 10,000, but the prevalence has increased to 10%. So we present this in a 2-by-2 table. 10% of 10,000 is 1,000, so we have 1,000 people with the disease. So that means 10,000 minus 1,000 is 9,000. Test is, sensitivity is 90%, so 90% of 1,000 is 900. The balance here is 100. Specificity is 90%, so 90% of 9,000 is 8,100, and the balance here is 900. Now, when we compute the positive predictive value, it is 900 over 1,800, and the NPV is 8,100 over 8200. And this is what we get. So while in the first case, the positive at 1% prevalence, the PPV was 8.3% and the negative predictive value was 99.8. When the prevalence changes to 10%, the PPV has increased to 50%, from 8.3 to 50. A 9 percentage point in prevalence leads to several percentage points change in PPV, but the NPV remains nearly the same. So the PPV changes markedly, but the NPV remains the same. This happens in situations where the people with the disease are the fewer ones. When the people with the disease are few in the population, a change in prevalence, let's say the people with the disease are 10%, a change in prevalence from 10 to 20% will result into a substantial increase in positive predictive value, but the NPV will remain the same. On the other hand, if a disease is very frequent and the majority have it, let's say 80% of the people have it, and the prevalence increases from 80 to 90, it is the NPV which will change markedly, but the PPV will remain fairly the same.